Hello, my name is Joshua Wong, and I will be presenting my Foundations midterm. So the first question is adding an introduction onto proofs and how it is different than other math courses using specific examples. So according to Wikipedia, a mathematical proof is a deductive argument for a mathematical statement, showing that the stated assumptions logically guarantee the conclusion. So proofs, according to my understanding, based off not just that definition, but everything I've learned in class so far, has been a detail-focused, thorough, logical argument based heavily on clear and concise communication skills. So detail-focused. I'll go into more depth later on kind of like those aspects, but I guess generally detail-focused is like being very knowing your definitions and thoroughly thinking through all the possibility space. And thorough as it also goes through definitions, logical arguments talking about having a process to your argument and structure it, and communication, talking about structuring that logical argument in such a way that makes sense to the reader, simplicity, so not showing all the pain that it took you to get there, just something that's easily understood and easily read through for people to understand what you're getting at. Uh, for other math courses, they usually rely on algorithms, calculations, very specific structure, and specific tools. So an example of this is integration by parts. Like it's kind of like an algorithm that you kind of like plug and chug when you have a specific problem in your like calculus journey, and you just kind of plug in the calculations. You don't understand kind of the why behind it, and you don't need to understand the why behind it unless you take like 4 to do that. You just kind of use it to solve a problem that you're currently working on through within that structure. And it's one of those specific tools. So there are I guess 5 key differences that I list here of proofs compared to other math courses. So generality, logical, the fact that they're logical, precision and clarity, creativity, and interdependence. Generality. So generality refers to the need to prove not just for one case, but for all of the cases. Calculus is one example compared to proof, so only computing the derivative of x squared is straightforward compared to proving the theorem that the derivative of x to the n, where x is positive, is n times x to the n minus 1. So rather than just like moving the exponent to the front and subtracting one over the exponent to get your derivative, proofs have to look at why this is true for every single case, for variables, for any value of n or x. So for an introduction to proofs, so the next point is logical. Sorry, off track there. Geometry is kind of like one of my examples of it, so that they're logical and that they follow a process of precedents that you look at based off previous definitions, kind of like a court case. So in this example, geometry, the Pythagorean theorem, you would just kind of use that and follow through with your equation. But in proofs, you would prove the theorem using geometric arguments. In this case, would be considered like precedent to the argument to frame your proof. Next is precision and clarity. So understanding, making sure that everything in your proof has a purpose for being there, and you define what you need to define with precise language, and that you're clear with how those definitions relate to your argument. So in this case, like in algebra, you may be allowed to skip a lot of intuitive steps to a solution. So like starting 1 plus 1 is 2. You might be able to skip a lot of addition steps and kind of jump to different parts of the problem as long as you get the right answer. But in proofs, there are no intuitive steps. You must justify everything explicitly. So in this case, you would want to define what addition is and what it means for two things to be equal to each other. And also, most likely define the space that you're in, so where you're drawing the variables or what space is there. And then the next point is creativity. So the fact that there are multiple ways to approach, but also to solve a proof. There's not just one solution to proving a statement is true or disproving it is true, or like more likely proving it is true. So one example that I remember is the conjecture that rational numbers are countable, presented by Dr. Kaufman in class the other day. So when he began his proof, he started with a combinatoric numerical based method, and he ended to prove the same thing with a graph-based method. So he's using two different methods, graphs and combinatorics and areas of math, in order to prove the same statement. It is one of the creativity aspects of proof writing. The next and final point that I had was independence. So the independence of writing proofs, in the sense of not having to follow these prescribed steps like you do, but it's also not a copy-paste solution for every single problem that you have. So one example that I had was the Morgan's law of unions versus the Morgan law of intersections, so proving those two statements. Now in class we saw that they were very different proofs. They weren't copy-paste proofs. They took completely different methods, like the case, one using two cases, one using one consideration, coming up with the proving those statements, but in different ways. So the next part of this presentation is a description of the steps of the proof writing movement and what purpose each step has to my assigned statement. So first step in the proof writing movement is develop examples. So you want to develop a series of examples that kind of really test your conjecture that you're trying to disprove by really exploring the space that you're working with that should be defined in the conjecture, or the space or universe that you're working in. So testing those bounds to see where this might break within the universe that is defined based off the name. Then you write your if-then statement. So like if this condition, then this condition must be true. You kind of put it in that form in order to get to step 3, where you extract your code, which is everything after the if statements and before the then, after the if and before the then. So what you know, like what you're basing your next part off of, and then you expand your know by using definitions to break it down into its like subparts and really like laying it out. And the next part is you extract your show. So you take the part after the then part of the if-then statement and extract that from the if-then statement. And then you expand on it, which is step 6. Expanding on your show in the same way that you expand on your know, breaking it down into its smaller parts and through definitions that you have, and using those tools to really get at the bottom of the raw statement that both those parts, the know and the show, are trying to make. And then you recraft your second draft of your if-then statement with those expansions in order to hopefully see a connection between your know and your show that you can then describe when you assemble your proof and eventually write your clean proof. So in this case, the statement that I was assigned to prove was that A and B be sets. Use examples to determine if it is true that the power set of A union B is equal to the power set of A union the power set of B. If it is true, prove this statement. If it isn't true, find a counterexample and prove a condition that may make it true. For example, restrictions of sets A and B, or one side that is a subset of the other. First, I define power sets above, so the set of all subsets in a set, and provide an example. Then I tried my first example, and it happened to be a counterexample. So I let A be the set of 1 and B be the set of 2 of just the value 2. So the A union B is the set of 1 and 2. Power set of A would be the null set and just the set of 1. And the power set of B would contain the null set and just the set of 2. And in this case, the power set of A union the power set of B did not contain the set 1, 2 that was contained in the power set of A union B. Therefore, they are not equal to each other. However, I consider, based off that counterexample of the first conjecture, to make a second conjecture that the power set of A union the power set of B is a subset of the power set of A union B. I also considered the conjecture of what if A was equal to B, but I ended up going with the first conjecture that I made about this subset, one being a subset of the other. So I revisit my last example showing that the power set of A union the power set of B is indeed a subset of the power set of A union B. I also provide another example where the set A and set B share a common value or elements, and I got that these two sets in this case were equal, but which by definition of subset also means that they're a subset. That the power set of A union the power set of B is a subset of the power set of A union B. So I write down my conjecture for the power set of A union the power set of B is a subset of the power set of A union B, and then following the first step of my proof writing with you, which was show examples. So I first showed examples. I found that my first conjecture was false, and I created the second conjecture and used examples to see if it was false, and I only found true examples as I went on. So then I dive into the second part of my proof writing review, which is step 2, which is write my if-then statement. So I say if X is an element or belongs to the power set of A union power set of B, and X belongs to the power set of A union B, I extract my no, which is X, that X is an element, X belongs to power set of A union power set of B. I expand on my no with the definition of union, saying that X is an element of Y's, such that Y is an element of power set of A, or Y is an element of power set of B. And then I expand it with the definition of power set, saying that X is an element of Y's, a set of Y's, such that Y is a subset of A or Y is a subset of B. And I simplify that to say that X is a subset of A or X is a subset of B. Know that has two cases. So that's my null note there. My next is my show, so saying that X is an element of power set of A union B. By the definition of power set, X is a subset of A union B. And by the definition of union, X is a subset of Y's, such that Y is an element of A or Y is an element of B. And I extract that X is a subset of A union B from this case. To create my second draft of my if statement, which is if X is a subset of A or X is a subset of B, and X is a subset of A union B. So from this statement, I can work on assembling my proof. I use two cases, when X is a subset of A and X is a subset of B based off my no, and say that, at least in the A case, that if I know that A is a subset of A union B, then X must be a subset of A union B, and therefore X is the element of the power sets of A union B by definitions of power set, etc. And that was all explained in my clean proof. And the reasoning for A is the same for the reasoning for B. To show that X is an element of the power set of A union B, and therefore the power set of A union the power set of B is a subset of the power set of A union B. So here's my clean proof of my statement. I start with my conjecture that for sets A and B, where P of A is the power set of A and P of B is the power set of B, the power set of A union the power set of B is a subset of the power set of A union B. I assume that X is an element of the power set of A union the power set of B. This means that X is an element of either the power set of A or the power set of B, or both by definition of union. Now I consider the two cases where X is an element of the power set of A, X is the power set is an element of the power set of B. In case 1, this means that, or X is an element of the power set of A, this means that X is a subset of A, and by definition of power set, since X is a subset of A, we know that X is a subset of A union B by the definition of union and subset. It follows that X is a subset of A union B, because anything that is a subset of A is a subset of A union B by the definition of subset. Therefore, X is an element of power set of A union B by the definition of a power set and subset, because X is a subset of A union B, and the power set of A union B is defined as the set of subsets of A union B. And for the second case, when X is an element of power sets of B, it acts similarly and pretty much in the same way, where if X is an element of power set of B, then by the definition of power set, X is a subset of B. As in case 1, since X is a subset of B, it follows that X is a subset of A union B by the definition of union and subset, as anything that is a subset of B is also a subset of A union B. Therefore, following the same reasoning with case 1, X is an element of the power set of A union B by definition of power set and subset. Therefore, for both sets of X where X is an element of the power set of A union power set of B, we have shown that X was the element of the power sets of A union B. And by the definition of subset, if X is an element of the power set of A union power set of B, then X is an element of power sets of A union B is true, then the power sets of A union power set of B is a subset of the power sets of A union B. So I use my proof checklist or proof quality control to check my proof. So the first one is checking if my proof defines all variables used, and that's underlined here. So like saying that sets defining A and B as sets and defining P of A and P of B as the power sets of A and B respectively, and also defining X as an element from power sets of A union power sets of B, or the set that set. My next is the color red, that my proof uses words to explain all algebraic transformations. So underlined in red, I can see that I show that because anything is a subset of A and a subset of B by definition of subset. So showing that how I came to find that X is a subset of A union B, and that was used in both cases. Next is the green statement, which is my proof states clearly where I am using the hypothesis to know. And that would be in my first line, which is the fact that I say I assume that X is an element from A and B. By saying I assume, I demonstrate that that is my no. I assume that is true. And the next part is the pink part, which is my proof states what method or approach I'm trying to use. So in this case, I'm using cases as my method approach. And then underlined in pink, I see this phrase, now I consider two cases, and then give my two cases and list them out, which I numbered them correctly. And then finally, I cite all definitions and theorems correctly and rely on the mathematical formulation. So that's the last one in orange. So there I underline in orange, I can see the definition of union, definition of power set, and the definition of subset being used sporadically throughout my proof. So thank you for listening to my presentation, and I hope you liked my proof. Have a great rest of y'all's day.